Today we're working on section 10.2, Real Number Exponents. This is a continuation of the last video where we talked about rational exponents. So when you add the irrational exponents into the set with the rational exponents, you end up covering all of the real numbers. So today we're going to be focusing on irrational exponents, which will complete the set of real number exponents for us. So we're going to start with some examples. In the first one, we're just going to simplify. So if we're given an expression like 2 to the 4 minus the square root of 5 power times 2 to the 1 plus the square root of 5 power. Now, these can be some pretty intimidating looking problems because we've got these bases and then these really wacky exponents with radicals and other things up here in the exponents where we're not used to seeing them. But I don't want you to be intimidated by the appearance of the problem. I want you to look at what's really happening. This is all familiar territory. So if you notice, we have the same base. This is a base 2. This is also base 2. We have worked with problems in the past where we have the same base and we're multiplying them. So to take you back, for example, if we have x squared times x cubed, well, we've done that before. These both have a base of x, so we keep the base, and then the rule when you're multiplying with like bases is to add the exponents. So in this case, we would have x to the 5th. We're going to use that same rule here. Even though these exponents look a little different, the rule is still the same. So the base is going to stay base 2, so we keep the base of 2. What we're going to do is we're going to add the exponents. So we have 4 minus root 5 plus 1 plus root 5. Well, this is another concept that we've covered before. When we were learning about radicals, we learned that radicals have like terms. So if we have negative root 5 and then we are adding a positive root 5, those just cancel each other out to 0. Then for the real parts, we add the real parts. So we have 4 plus 1. I'm going to keep my base of 2. 4 plus 1 gives me 5. Negative root 5 plus root 5 cancels out to 0. So the radicals go away. So all I have to solve is 2 to the 5th. And then from practice or using your calculator, you can see that 2 to the 5th is 32. So even though it started out with these crazy intimidating exponents, we were able to simplify them. All right, let's try another one. If we have a quantity 5 to the 2 root 3 power, and we're going to raise that to the root 3 power. So again, this is a familiar rule. When we raise a power to a power, the exponent rules say that we multiply powers. So we're going to keep the base of 5. We're going to multiply powers. So we're multiplying radical expressions. We're going to multiply the outside part times the outside part, or the coefficient. So 2 times 1 gives me 2. And then we multiply the inside part. So root 3 times root 3 is root 9. Now that should be kind of standing out to you. Root 9, you know, is a perfect square. So root 9 is 3. So we have 2 times 3. So this actually gives us 5 to the 6th. And then using a calculator, we could find that that is 15,625. All right, one more. If we have 3 to the 2 plus root 7 power all over 3 to the 2 minus root 7 power. Again, this is a familiar rule, even though it's not a familiar looking problem. We have a base of 3 and a base of 3. The bases are the same. This is a quotient or division problem. When we're dividing with like bases, the rules for exponents tell us that we combine into one base by subtracting the exponents. So we're going to rewrite this as root 3, the base 3, and then we're going to have this top exponent, 2 plus root 7, minus the bottom exponent, 2 minus root 7. All right, be careful with your signs here. This is -2, and then this is going to be minus a -7 in just a second. So for the real parts, we have 2 minus 2. Well, that gives us 0. Then we have positive root 7 minus negative root 7. Well, when you subtract a negative, you're actually adding. So we have one of these, we're going to add another one, so we have 2 root 7. We don't need that 0 there, so we have 3 to the 2 root 7 power. And that's all we're going to do with that. That is simplified. Let's talk about what it means for something to be an exponential function. So this is the definition of exponential function. Exponential function defined. So if b is greater than 0 and b does not equal 1, the function defined by y equals b to the x power is called the exponential function. Exponential function with base b. So b is the base. This is going to be a number. X, the exponent, the variable, is in the exponent position. So by definition, we're working with an exponential function when we have a variable in the exponent's position. This is different than when you have the variable as a base and you have a number as the exponent. We've swapped roles here. The number is going to be the base. It can't be 0 and it can't be 1. It has to be greater than 0 and it can't be 1. And the exponent is going to be a variable. That's what makes an exponential function. In your book, it talks about what the graphs of exponential functions look like. We will look at that more closely in another section. So you can refer to that on page 460 if you're just curious. It's kind of cool if you're watching this right now in March of 2020. Exponential functions are pretty cool because they model the type of growth that we're seeing with this virus, the COVID-19 virus. So if you've been noticing them talking about the virus and the curve of the virus, I'll just go ahead and show you. A positive exponential function is going to have this kind of growth pattern. So it starts out kind of small, but then it grows very quickly, very fast. And then a negative exponential function is going to fall this way. So it starts out big and then it falls this way. So we'll talk more about the characteristics, the specific characteristics of these exponential graphs a little later, but I wanted you to see just this basic shape, this exponential growth, growing very rapidly here. All right, the other important thing that you need to know from this section is how to solve exponential equations. So in your book on page 460, there's a gray box that says solving exponential equations. I would highly recommend that you copy those points into your notes and refer to them when you're solving equations. I'll read them to you quickly here. Step 1, express each side of the equation as a power of the same base. Step 2, set the exponents equal and then solve. Step 3, check the answer. So we're going to do several of these together right now, and I'm going to explain to you each of the steps, what they look like. So for this example, we're solving. Now you have to be a little manipulative here. You have to be willing to change some things around. So we're going to start with 3 to the x power equals 1/9. So first of all, we've got a 3 on the left side, we've got a 9 on the right side. These are not the same base. Earlier in the lesson, we were looking at examples where the bases were the same. These bases are not the same, but you should be thinking to yourself, ooh, 3 and 9 are not the same number, but 9 is a power of 3. So it is possible that I could rewrite 9 so that it looks like a 3. And so that's the first step. Express each side of the equation as a power of the same base. We're going to rewrite this so that they have the same base. The trick for that is that you want to write the larger base as a power of the smaller base. So that's something to remember if you get stuck. Write the larger base as a power of the smaller base. Now, it can go the other way, but most of us, it's more natural for us to do it this way. So this is just a tip. It's not a hard and fast rule. So what we're going to do is we're going to rewrite this 9 as a power of 3. 9 is 3 squared. So I'm going to have 3 to the x power equals 1 over 3 squared. I haven't changed its value. 3 squared still equals 9. I have not changed its value. I've just changed the way it looks. Now, the next thing we want to do is we've got 3 to the x power over here. It's in the numerator. Even though it's not showing that this is a fraction, this is in the numerator. I would also like for this power of 3 to be in the numerator. It's just easier to work with if we've got numerators compared to numerators. So if you remember from last chapter, when we are working with exponents, we can move things around in the fraction by changing a positive exponent to a negative exponent. So on the left side, this is going to stay the same, 3 to the x. On the right side, I'm going to bring this up to the top by making it 3 to the negative 2 power. Again, that's the rules for negative exponents. We covered those in a previous chapter, so if you want to look back at that, you can. All right, now we've gotten what we want. We have a base 3 over here and a base 3 over here. So this is kind of a logic thing. You have to think this out. If I have 3 to some power on the left and it's equal to 3 to some power on the right, it must be true that the powers are equal to each other. So this is step 2. Set the exponents equal and then solve. Once you have the bases the same, you can just bring down the exponents and set them equal to each other. So we can set x equal to negative 2. And now that's our answer. You can check it. 3 to the negative 2 power should equal 1/9. We're testing that. 3 to the negative 2 power is 1 over 3 squared. 1 over 3 squared is 1/9, and 1/9 does equal 1/9. So that checks. So our answer, our solution, is x equals negative 2. That one was pretty simple. So these are going to get a little more complex as we go. Let's look at the next one. If we have 4 to the 2x power equals 1/2 to the 1 minus 2x power. All right, so back to step 1. Express each side of the equation as a power of the same base. I have a base 4 and a base 1/2 because 1/2 is what's being raised to the power here. But really what I'm thinking about is a 4 and a 2. How can we rewrite this so that they have the same base? Well, we want to write the larger base as a power of the smaller base. I'm going to rewrite the 4 because I know that 4 is the same thing as 2 squared. So I'm going to rewrite this 4 as 2 squared. But then I also have to keep the exponent that was already there. So the 2x that was already there comes down also. Now I'm going to go ahead and do one step on this right side. I have 1 over 2. I would like that 2 to be up in the numerator. So using the rules for negative exponents, I can bring 2 up to the numerator if I give it a negative exponent. Right now it's 2 to the first power. So if I want to bring it up, I'm going to make it 2 to the negative 1 power. And then it still has its original exponent, 1 minus 2x. Okay, so now we've got base 2 on the left, base 2 on the right. Once you've rewritten it with the same base, then you can set the exponents equal and solve. So I'm going to bring down the exponent here. Now, remember your exponent rules. A power to a power means you multiply powers. So this is coming down as 2 times 2x. Over here, I'm going to bring down the exponent. Same thing. A power to a power means you multiply. So I'm going to bring this down as a multiplication problem. Okay. 2 times 2x gives me 4x. Here I'm going to distribute the negative 1. Negative 1 times 1 is negative 1. Negative 1 times negative 2x is positive 2x. Now I've got this little equation. I've got x's on the left and x's on the right. I'm going to move these, so I'm going to subtract 2x from both sides. 4x minus 2x gives me 2x. 2x equals negative 1. Divide by 2. And x equals negative 1/2. All right? And you can go back and check that. Let's try another one. If we have 5 to the 3x power, and that's equal to 1 over 25 to the x minus 1 power. All right, so by now you should be thinking, looking for a like base. Express each side of the equation as a power of the same base. We have 5 and 25. You should recognize that 25 is 5 squared. So this is the one we want to rewrite. Write the larger base as a power of the smaller base. Don't try to rewrite the 5. Rewrite the 25. So we have 5 to the 3x equals 1 over 5 squared raised to the x minus 1. Now, using the rules for negative exponents, I can bring this up from the denominator by making it 5 to the negative 2. So 5 to the 3x equals 5 to the negative 2, still raised to the x minus 1. All right, we've accomplished the first step. We have the base 5 on the left, base 5 on the right. Step 2, set the exponents equal and then solve. So I'm just bringing down the exponents. 3x. Here I have a power to a power, so I'm going to multiply negative 2 times x minus 1. So 3x, here I'm going to distribute negative 2x plus 2, add 2x to both sides. 3x plus 2x gives me 5x. 5x equals 2, divide by 5, and x equals 2/5. You could also if you wanted to, you could maybe check this on your calculator. Put in 2/5 in place of the x and work out get a decimal approximation on the left. Put in 2/5 in place of the x, get a decimal approximation on the right. You're comparing, does the decimal approximation for this side equal the decimal approximation for this side? They should be a match. That's how you know that's a check. All right, let's try a couple more that look a little different but are actually still kind of the same thing. If we have the cube root of 32 equals 2 to the x power. Now, if you don't know your powers of 2, I would recommend that you study them. Study them up to 2 to the 5th you should recognize at first sight. Your powers of 3 you should recognize up to 3 cubed. For 4, you should recognize up to 4 cubed. And 5, you should recognize up to 5 cubed. Those are the ones that get used the most often for these. For your other numbers, recognize your perfect squares. So this is going to use a rule that we just learned in the last lesson. So we are going to take care of this radical by rewriting it as a rational exponent in just a minute. We're not quite ready. I was jumping ahead. So first we need to decide on what our base is going to be. We have a base 2 and a base 32. We want to rewrite the larger one as a power of the smaller one. So 32 is 2 to the 5th. So I'm going to rewrite this as the cube root of 2 to the 5th equals 2 to the x. Now, in the previous lesson, we learned that you can rewrite a radical expression as a rational exponent. You keep the base 2, and then it becomes a fractional exponent. Do you remember where the root goes? Just like a tree, the root goes on the bottom. So the power 5 goes on the top, the root 3 goes on the bottom. So the cube root of 2 to the 5th is equivalent to 2 to the 5/3 power. And then over here we have 2 to the x. All right, we've completed step 1. We have like bases on both sides. So now we're going to bring down the exponents and set them equal. 5/3 has to equal x. And that's our answer. Last one for today. I'm trying to show you a bunch of different types of problems. We've got 9 to the x minus 3 power equals 27. Now for this one, 9 squared does not equal 27. 27 squared does not equal 9. There's no way that we can rewrite these two numbers in terms of each other. So we have to think of this a different way. They do have a power of 3 in common. 9 can be rewritten as a power of 3. 27 can also be rewritten as a power of 3. So that's what we're going to do for this one. When we rewrite these, we're going to rewrite them both as a power of 3. So 9 becomes 3 squared and still raised to the x minus 3 power. 27 becomes 3 cubed. Now remember, we cannot change their value. I'm not changing the value of the 9. 3 squared still equals 9. 3 cubed still equals 27. I'm just changing the way they look. So now I've got base 3 on both sides. That's step 1. Step 2 is bring down the exponents. So I've got 2 times x minus 3 equals 3. I'm going to distribute here. So 2x minus 6 equals 3. Add 6 to both sides. 2x equals 9. Divide by 2, and x equals 9/2. There are lots of tricks with these. So for each question, take a minute and look at what you have to work with. What power is standing out to you? Are you looking at numbers that are powers of 2? Are you looking at numbers that are powers of 3? Maybe powers of 5? Look for where you think that common base is going to be, and then rewrite your bases so that they're the same base raised to a power. Once you have your bases the same, then it's really easy from there. You just have to bring down the exponents. You have a nice, usually linear equation. As we get a little higher, some of these might not be linear, but usually it's a nice linear equation that's quick to solve. If you have any questions, please send me an email. Hopefully this video will help you. These questions may cause frustration. Please do not give up quickly. Spend a minute looking at the problem. How can you rewrite something in the problem? Look for something to rewrite. Once you rewrite, that usually will tip you off to what you need to do next, and it kind of cascades from there.